Alright, welcome back. Today I'm going to be completing part B of homework 3 for process dynamics and controls. What we're going to be doing today is we're going to take this transfer function we derived in part A for a single gravity drain tank, and we are going to apply it to a system of 3 gravity drain tanks in series, the same system we've seen a couple times before, with a proportional only controller, but using this transfer function applied to the 3 tanks. And so to give a little bit of a visual way to see how this looks for 3 tanks, we can first consider that this function essentially looks like a Qn going into our transfer function, which produces our height. And this is for a single tank. So it's fairly trivial to apply this to 3 tanks. What we're going to do is we're going to say that this Qn produces our H1 in our first tank, which we can then multiply that by 1 over k to give us Q1, which we can again multiply by our transfer function, k over tau s plus 1, to give us H2, we can multiply by 1 over k again to give us Q2, which can be multiplied by k over tau s plus 1 to give us our H3 island. And this is in essence our process here, played out visually as compared to our initial one. And as I was saying, we're multiplying these out, so what this is going to take the form of is H3 is going to equal Qn times our k over tau s plus 1 cubed, as you can see we're multiplying out 3 of them, times r 1 over k squared. Moving on from here, we need to find our closed loop so we can get that closed loop transfer function. And what is that closed loop? Like I said here, we've got our process that we've circled here. So as we showed before, we've got a Qn that is going into this process up here, which then goes on to produce our H3, our final height. But as we mentioned before, we're using a proportional only controller to control this, and the first step for this proportional only controller is to check our heights. So we're going to need a transfer function that's going to look at all of our heights so that it can go on to tell our controller how it's going to need to change our Qn in order to match our set point. So this transfer function that's reading our heights is going to go directly into our controller, our proportional only controller, which is going to be controlled by our controller transfer function here. And that controller is going to be determined by a set height for our H3. So what are each of these blocks? Well, this first one, this is our process transfer function that we discussed up here, our GP. This down here, we're calling this our GM. That's our transfer function, as I said before. It's going to be reading our heights and telling our controller how to change them. And the gain on that controller is going to be determined by the controller transfer function GC. And the difference between this set point here and this controller transfer function, that is going to be our error. So, looking at this, how are we going to define this error? Well, our error is going to equal our H3 times our transfer function that is reading our heights, because that's what's kind of the translator between our H3 and how our controller sees it, our GM transfer function here, GM. And then, of course, we're going to subtract the set point. That's for any general error function. And we can also say that H3 equals our GC times our GP, our controller transfer function, our process transfer function, times that error we were talking about. And plugging in our value for our error, we figured out up here, we get that H3 equals GC GP times H3 GM minus HSP. Now clearly what we need to do here is isolate our H3. Get it all on one side. So looking at this function again, our H3 equals GC GP times H3 GM minus HSP. We can multiply this out to give us H3 GM GC GP minus GC GE HSP. Then, if we bring this over to the other side, we can get an H3 minus H3 GM GC GP equal negative GC GP HSP. Then, isolating our H3, we can get this out of the way. H3 times 1 minus GM GC GP. It's going to equal minus GC GP HSP. Then, dividing this over, we can get that H3. I'll just make this a board. It's going to equal minus, or actually let's rearrange this. Get rid of this minus. H3 is going to equal GC GP over 1 plus GP GC all multiplied by HSP. And this right here is our closed loop transfer function for our 3 gravity drain tanks. To make it a little bit easier to understand this, we can rewrite this function as h3 equals our g forward over 1 plus our g for the open loop. So as you can see, our g forward, that is our GC GP, going forward before the feedback. That's why it's called g forward. It's divided by 1 over the open loop, GC, GP, GM, in an open loop. So, now that we've got our transfer function for our 3 gravity drain tanks, we can go ahead and move on to the next part of the problem. Alright, so now that we have our transfer function for our 3 gravity drain tanks, we can go ahead and use the final value theorem to show that with proportional only control, the height of the third tank will never reach our set point. And there will always be an offset between the two, but we'll realize that as our controller gain K goes up, that offset will decrease more and more the greater our controller gain is. So, to get started here, let's start off by defining the final value theorem. That is probably important. So, the final value theorem states that the limit as s approaches 0, the Laplace function sy must equal the limit as s approaches 0 of the original function y. And applying this to our function up here, we can get that the limit is s approaches 0 of sh is going to equal the limit as s approaches 0 of our GC times GP over 1 plus G E G C G M, all times our HSP. And it will be helpful here to consider that our set point is a step change in our height, which looks something like this. And this distance here, that step change that our set point is initializing, can be defined as A over S. So, subbing that into our function here, you can see that the limit as s approaches 0 sh equals the limit as s approaches 0 of g c g e over 1 plus g p g c g m. Now we're going to apply that A over S, which will allow us to cancel this S as well as the S in this denominator, leaving us with the limit of big H equals, this approaches 0, H equals the limit, so S approaches 0 of A times our G, C, G, P over 1 plus G, C, G, M, G, P. Now we can apply another finding that we found earlier in this problem, our GP, which is the only transfer function we know definitively, which is this k over tau s plus 1 cubed times 1 over k squared. So taking this, we can say we know our GP, we're just going to cancel out these variables here, equals k over tau s cubed plus 1 cubed. And since we've got this s variable only here, if we go ahead and take the limit of this right here, s approaches k over about s plus 1 cubed, we can see that as s goes to 0, this value in the bottom here approaches 1, meaning that limit as s goes to 0, this part right here, our GP, is going to approach k. And plugging that into our expression here with these two GPs, we're going to get that the limit as s goes to 0, h is going to equal the limit as s goes to 0 of a GC times k over 1 plus GMGC times k, all times are a, which is that set point jump we were talking about. And taking a look at this function, we know that this value right here must always be positive. Must be non-negative, meaning that this will always be bigger than this. This value here will always be greater than 1. So that little part there will always be greater than 1 because this is k multiplied by 2 and then adding 1. So it's just the way it works out. This will always be less than 1, as the denominator will always be bigger than the numerator, which satisfies the first part of this, where you can see like our h3 and our set point jump. Our h3 is never going to hit this set point, as this is always going to be less than 1, a positive less than 1 fraction. So there will always be an offset where our set point height will always be a little bit lower than our actual height will always be a little bit lower than our set point height, as described here. And furthermore, to prove that this is relative to the controller gain, you can take the limit as k goes to infinity of our GC times our k over 1 plus GM GC times our k. And looking at this, as that k approaches infinity, proportionally this 1 matters less and less and less and less. It's just adding 1 to a humongous number as our k increases, meaning that this value approaches 1. So our set point, our h3 is going to get closer and closer and closer and closer to our set point, to where as that k increases, if our k is infinity, our set point would be, or our h3 would be at the exact height of our set point. But functionally, this is saying as k gets bigger and bigger and bigger, that offset is going to decrease, which is the proof we were looking at for the second part of part B. I believe that is the end of part B for Round 3 for Process Dynamics and Controls. I believe in the next part, we're going to go ahead and code this up a little bit so we can see a more real example. So we'll see you in the next one.